Every year, millions of tons of plastic waste end up in our rivers and lakes. Over time, these plastics break down into tiny particles called microplastics. They are invisible to the human eye but extremely harmful, not only to fish and marine animals but also to us humans through the food chain. Now, here's a real problem. Detecting and monitoring these microplastics is still a huge challenge. Traditional methods are slow, manual, and can't provide real time information about water quality or pollution levels. That's why we have worked with an innovative idea, a robotic floating platform powered by sensors and machine learning. The goal is simple: scan the water, detect pollution, identify plastics, and give live updates for authorities to act faster.
As a request from Ministry of Earth Sciences, we have developed a robot for monitoring chlorophyll and plastic pollution in aquatic environments. Here is the hardware setup of our project.
Sensor, color sensor, and Arduino. The turbidity sensor is used for detecting the cloudiness of the water, and then amidst and the color sensor. And if we pass UV LED, we'll get. If we pass the UV LED, the microplastics present in the water excites the fluorescence, and the color is detected by the color sensor, and we are able to visualize the values in the serial monitor. As we can see there, the we can this data is sent to an app. We have developed the app for getting the data of the RGB and turbidity sensor. We have also developed an ML model where this data is processed, and then the classification of the plastics is also obtained in the app. This is the most unique thing of our project. We have, I have also used smartphone camera for capturing the image, and this will be sent to the app. In the app, we will be obtaining the classification of the plastic and the turbidity and the color RGB fluorescence fluorescence value, and then this using this data we can classify whether the plastic is PET or PS or PP, etc.
At its core is a machine learning model. It uses hyperspectral data to fingerprint and quantify specific pollutants. The data is collected by the autonomous floating platform, and all sensor input and the ML model analysis is instantly pushed to our user friendly mobile app in real time, giving environmental managers real time risk maps for rapid response to both plastic and chlorophyll contamination.
So at present now we are looking at the design and test of a low-cost RGB sensor for online measurement of microalgae concentration with a photo biodirector. So this is one of the paper that we have taken as a baseline base for our project that we are carrying on. So as we come down, we can see them using the materials and methods. In this, we can see them. They propose a biomass online measurement method that use of a low-cost RGB light sensor to estimate the turbidity of the medium containing the microalgae, meaning them detecting the microalgae using this RGB sensor. So as we come down, we can see them their structure. So they are basically use RGB sensor and Arduino, same as V. So come down. So we can see the equation they have scientifically uncovered to um, further relate. So this one relates luminance, turbidity, and biomass relationships, which gives an additional layer of biology and edge to the innovation where we are carrying on this project. So this is a scientific and biological stand behind. So we will go to the next research paper. The next research paper is this: the low-cost turbidity sensor to determine eutrophication in water bodies. So this research paper supports the usage of turbidity sensor. Um, and then at present we can see that the use of interval 98 can determine the turbidity of an error of 7.4 which NTU readings higher than 12.7, and the use of the light of 180 degree can measure the solid concentration with an error of 1140 degree, 1.40% it is. So these error standards are being practically it's like it shows the practical approach that nothing is perfect. I mean it shows the error as well. So mathematically we had to endure them as well. Mathematically we have to take them into consideration as well. So we come back down. So we can see, so this is the ratable work they are doing. So once we go down next to the machine learning model. So after seeing those research papers, we have an idea of using RGB sensor and turbidity sensor. So next we are going down to the machine learning model. So in this machine learning model, I can explain each and everything. So we can see them for pre-processing. We are using the scikit-learn's standard scalar label encoder, and then the scikit-learn model selection. We use the train to split. Of course, the ratio will be discussed further when the line comes up. Scikit-learn metrics have the accuracy score, classification report, and confusion matrix. We are using these three to determine how good is our model. So when we come down, we can see the XGB boost and Seaborn models. We both are using a hybrid model. So when we come down, um, uh, for for the heavy model to run in laptops, we have to define a chunk size. So I'm running this model and the data set in a chunks. So we can see the program is run for that. So this one, and then yeah. So these are all the access points for the data set we synthetically created. So we go down. Then I can see you can see the model's execution here. The model is equal to XDB, the XDB classifier. So this model and the state has been given them. And then if we come down, yeah, as you can see, so confusion matrix been calculated here. Predictions and these variables have been executed in the previous lines. So we have even given them sample cases as well. So here we go. Yeah, we given sample predictions and yeah, same things. And then the sample accuracy will be calculated here in this line. So I'm going to run this a test run. Okay, so we can see them calculating almost perfect 99.9%, and when it comes to samples, and then when we come down, we can also see them getting a 100% here. So it is. You may guys may wonder, is this a overfitting model or something? No, it's not overfitting. It is just it. The values are not overbounding for plastic and algae, so we can definitely distinguish them. And then for further class in plastic, the research is going on. At present, our model just detects algae and the plastic, and then distinguishes them using the NTU values that they get from turbidity sensor. So basically, turbidity and RGB sensors are used, and their values are used to distinguish algae and plastic. There is no bounding between them. That's the one. There is no overlapping between them. As per the values concerned, the ranges has been taken in such a way scientifically that they won't have a overlapping, or scientifically they don't overlap to begin with. So there is no noise in this model. So which gives them a 100% accuracy, not because of overfitting, but it is the actual thing. Thank you.
Hi, so this is our app. We have a capture or upload option and a history option. When I click capture or upload, I'll be able to upload an image, or if I'm on a phone, I'll also be able to capture an image on the spot. I'm gonna upload this image right now. It has some microplastic present in it. Analyze the sample and shows that microplastics are detected. In this case, we can see that the particle count is 135 particles per liter, and we can see the turbidity analysis and the chemical analysis and also the particle details, and it also shows us the detected microplastic type. We have a test new sample button here so that it will take us back to the home page, and I'm also able to see the history of previous results here in the history tab. In the end, our robotic platform not only monitors but it empowers informed immediate action to preserve our most valuable resource, which is water.